Okay, so let's start then. Last time we talked about, started talking about probabilistic prediction. And so if you recall, we had this Titanic data example. And we did, so we just look at it and try to predict like the binary response for y based on the binary set. So that was sort of the simplest classifier that we can imagine. So we talked about the probabilistic framework. So we model the feature as x, the random variable, and y, the response or the target as y, another random variable. And there should be some relation between them. So we model this as a joint distribution. And then we assume that we know this joint distribution first, like as the first step, which is going to be, or at least can be described by 4 numbers. So the probability that 6 is one of the levels and y is one of the other levels, it gives you 4 combinations, and if you have the probability of all the 4 combinations, then you can calculate all the events in terms of these 2 random variables. So we started off with the most basic classifier, which is the one that ignores all the features. We call it majority rule. So if I don't see any features, I predict y just based on the marginal distribution of y. And it's easy to calculate from this. Hopefully everyone remembers or like reviews probability. So from this table, it's easy to calculate the marginal distribution of y, and then you decide, for example, because with high, the probability of not surviving is higher. So you always output not survive, 0. And then we added the feature x here, and then intuitively we argued that now we should look at the conditional probability, the probability that y survives, y is 1 or 0 given x is equal to x. And because the response is binary, you just have to look at one of these probabilities. The other one will be 1 minus this. So we looked at the probability that y is equal to 1 given x is equal to x. And with the basic probability, you can calculate this conditional probability. And it turns out that if x is female, the conditional probability of survival is like 0.72. If they're male, it's 0.19. And again, intuitively, so when they're female, we're going to predict that they're going to survive because the probability of survival is higher. And if they're male, predict that they're not going to survive because the probability of not surviving is the probability of survival, the probability of not surviving is the opposite of 1. So this gave us this F2 classifier, and we saw that you can think of this as the argmax of this quantity, the probability of y equals v given x is equal to x, as v varies in all the decisions. And decisions here are like the set of decisions is 0, 1. So we have just 2 decisions, but you can also imagine you could have multiple decisions. The same idea actually applies there. But let's focus on the binary case. So I hope this notation is clear. Argmax. It's like the mathematical notation to use to say that we choose a decision which gives us the maximal conditional probability of y being equal to that decision given x. Alternatively, we can minimize the probability that y is not equal to the decision, but in this case, or in general, this is the case. If y is not equal to b, the probability of y is not equal to b is 1 minus the probability of y is equal to b. So to minimize this probability, and the decision that minimizes it gives us the optimal, this classifier. And with them, we discuss how to evaluate the classifier. And a natural measure is accuracy, which is saying if I pick a random pair features and the target from the probability solution, what is the chance that my prediction, which is y hat, this chi-square f applied to x, my prediction is equal to y. That's the probability to a correct classification, sometimes referred to as accuracy, is a good measure. Like equivalently, we can look at 1 minus the accuracy, which is misclassification risk or the error rate. And then we calculated this for the majority rule, which turned out to be simple, would be 0.38. And for the other rule, using two approaches. I think one was using joint distribution, AC, I guess. Yeah, so that was first solution. And the conditional one, someone else mentioned, in the class. Okay, so what was your name again?
Nacho.
Nacho, okay. So I'm gonna learn your names like more like it's like I'm training. Like my neural net is not that strong anymore, so I have to like get more samples. So Nacho proposed to do the other way, which is like conditional X, and this is interesting in the sense that it also reveals what the optimal classifier should be. Okay, so we condition on X. When we condition on X, there is the law of total probability. And the reason why it's useful is because once I condition on X, the decision is completely determined. So once I condition on X, for example, female, whatever the classifier is doing, this is going to be either 0 or 1. It has to decide which rate it goes. And so this is deterministic, and this would be the conditional probability of y not equal to something given X, which we can calculate from the choice. So anyone remembers why this is useful to yes, or like argue about the optimal classifier? How do I get from this kind of expansion to the optimal classifier? So this is like the usual probability. Anyone remembers how we argued what an optimal classifier should be?
Minimizing that expression.
What expression? So you want to minimize this.
Yeah, like picking the f2 of f that minimizes that probability.
Right. Okay. So we have these, like, let's say, two terms, and so the thing to notice is that these parts are changes. These are not up to us. And these two terms, the conditional ones, are sort of independent of each other because this depends on what value I choose for f2 of f. This depends on what value I choose for f2 of m. And so I can deal with these separately, and then for this one, I'm just going to pick the value for f2 of f. Application, but this is female. That value of f2 of female is either 1 or 0. I'm going to choose whichever one that minimizes this quantity. Okay, then I'm sure that this is small as possible, and I'm going to do it for this as well. This one is going to be f2 of male, which has nothing to do with f2 of female, so I can do it separately for each term. For each term, we minimize the and if you argue it this way, think about it, it gives you that in general, what you should do is do exactly this. So for each X, you're going to go maximize or minimize basically probability of y is not equal to b. Okay, so the optimal rule would be what would be the optimal rule? the above shows that the optimal rule, or like optimal classification rule or classifier, is the one that, let's call it star, minimizes the probability that y is not equal to d given x is equal to x for any possible decision. So given x is equal to x, I'm going to look at the probability that y is not equal to d. D is just a dummy variable, stands for decision, let's say. That would be like the value of, basically this stands for the value of f of x. Okay, or f star of x. So it's a dummy variable, and we'll check all possible choices, and then the one that minimizes it has to make a decision for that particular case. Okay. Sounds good. So if you understand this, the same argument applies even if x was continuous, more complicated. Because that law of total probability, so what if x was continuous / like more complicated? So let's say it's continuous, has a density, has density Ex. What happens is that I can still condition. So probability of y not equal to f of x, this is the error that I want to minimize. I can write it as integral p y not equal to f of little x, condition on x is equal to x, and then what? Times
f of x.
P. This is the density, right? So the density, this is like the probability, like this part is like the probability that random variable x takes value near little x. So this is just a weighted average. So in the discrete case, this would be like continuous case. This would be just P of x. This would be PMF, probability mass function. Here, this would be density, probability density function. So continuous case, discrete case. Same thing, probability. This is discrete. So this one is exactly what we had before. So this is the PMF, basically are these two. So if you're summing over all possible values, the probability that this thing is probability mass function is the probability that x is equal to x. So this is the discrete case, which we know. This is the continuous version is very similar. This is like the sum with an integral, and then these weights tell you the probability that you observe that x, basically. In the continuous case, you probably know that probably observing the particular value is 0, but that's where the density, like then the math comes in. Probability of being very close to x. Px, dx, and then sort of just integrate. Does that ring a bell? So this formula is, both of them are like laws of total probability. Law of total probability. If you look at the notes, I actually write it in a way that covers both. If you know measure theory, you can write an integral with the general measure. Maybe get to that at some point, but you don't have to worry about that. And so this formula, for example, each term here is up to us. So this part is up to us. This other part is not up to us. So I can't control this. I can control the yellow part. And then for the yellow part, I can like pointwise minimize it. For every x, again, I'm going to choose f of x that minimizes this. So then if you think about this, it's just give you this exactly. Okay. The exact rule applies in this case. So this argument that we did produces the structure of the optimal rule, or sometimes Bayes rule, in the very general setting. Does that sort of make sense? So if it doesn't make sense, just go back to this argument. Here we just have two cases. Here we just have infinitely many cases, but we deal with each like one separate. So what I should choose for this particular x, the decision that minimizes this. For another x, the same thing. For another x, it's the same thing. And so you deal with them separately, and then it's easy to argue that this should minimize the probability of error because we are minimizing every possible term. Or if you want to think about this, every possible term in the sum. Sounds good. Questions? Comments? Sure. Always ask questions. But before we move on, so this might be a little bit abstract, but hopefully you understand now where this comes from. So this is what I'm going to focus on for a while. The only thing that you need to calculate, you needed to be able to calculate this is this conditional probability, which we assumed we know because we know the joint, then it's easy to calculate this. So our job would be to actually approximate it or estimate it in practice. But before we move on, I just want to point out that the notion of how good a classifier is, as I mentioned, is sort of subjective. If you want to optimize your accuracy, equivalence classification rate, this is what you get. But you can change your measure of performance. Okay, so you can do something a bit more general. For example, I can define a general loss. So I can have a general function that tells me how much I lose if y is the true label and y hat is my prediction. Okay, so the one that we've seen so far that leads to accuracy is actually called the 0-1 loss. So so far we looked at this loss. I'm going to write it as indicator y hat not equal to y. So it's like 1 and then braces, and in the braces y hat not equal to 1. So this means whenever this condition holds, y hat not equal to 1, this is 1, and otherwise, which means if y is equal to y hat is equal to y, it's 0. Okay, so you don't pay any price if you correctly specify the label, but you pay price of 1 if you don't. So if you pick this loss, then what do you think I can, like, can anyone tell me what the accuracy or like the misclassification error would be in terms of this loss? How can I write? Yes.
The one that we saw previously.
Yes, this one. So this is like probability of y not equal to y hat. Can I write it in terms of this loss?
Law of total probability.
Sorry?
Law of total probability.
Which would be, in this case, what would it be? Law of total probability. This is already a probability, so you want to condition. So usually, like with law of total probability, you condition on something. You can say, okay, so the thing that I wanted to like do is like, or maybe you can like elaborate. So how do you like, let's say I have like L of y and y hat is equal to y not equal to y hat. How can I write this in terms of this guy?
See, expectation.
Okay, yes. Okay, that was what I was looking for. So if you think about this, this guy is another random variable because they're both random variables. So y and y hat are random variables. So this is another binary random variable. Right? So it's either 1 or 0. And the expectation of this random variable would be what? So expectation of L of y and y hat is so it's a binary variable. So how do you calculate the expectation of binary variable?
1 times the probability is y not equal to y not.
Right. Okay. So 1 times the probability that this guy is equal to, let's say, write it like this, is equal to 1, which is just y not equal to y hat, plus 0, right? Times the probability that ly y hat is equal to 0. Right? Which is just y is equal to y hat. But this part is 0, definitely. So you get that the expectation of this loss is really the probability of error. Okay. And generally, the expectation of indicator variable is the probability that it takes value 1. Okay. So our measure accuracy or from this classification rate can be written as the expected value of this 0, 1 loss. Okay, so the terminology loss is what appears in the statistics or decision theory or like theoretical machine learning. So you pick a measure of loss and then you look at the expectation of the loss, which is sometimes called risk. And then your measure of performance would be this guy, the risk. Which you can write it as L of fx and y. Because y hat is this. So this is going to be our measure. So this is a bit more general. Now I can change L and I get a different measure. Okay. And then with the 0, 1 loss, I get this classification rate that we have. Okay, but this is a bit more general. Does that make sense to people? So that's how you can generalize. The 0, 1 loss, you can think of it as, because these are binary losses. So I have either y here and y hat. There's like 0, 1, 0, 1. I have to specify what values, like what costs or what losses I assign. If I'm correct, these are going to be 0 and these are going to be 1. So when they mismatch, result. So this is the compact version of writing the 0, 1 loss. But I mean, in practice, there's potential. Usually you don't want to assign losses. You can assign losses if you make correct decisions. That's also possible. You can make these non-zero. But usually you don't do that. See, these are 0, but they can have different costs here. So this guy can be like 0, 1. Well, let's say cost 1, cost 2. 2 different numbers here. Okay, so like if they're the same, it's equivalent sort of to this. But if they're different, I assign asymmetric losses to the kind of error that I have. So for example, in this case, I could have, let's say, 0.1 here, 0.9 here, or they don't have to sum to 1. Or so let's say this is 7, this is 3. What it does is it's saying that if the true label was 0, then I create it as y, I could price as 7. If the true label was 1, then I create it as 0, I could price as 3. So it's less costly to make a mistake on the right decision than on the wrong decision. Sorry, I made it. So it's more costly to this is sometimes called false alarm. So if there's nothing there, zero usually like condition none. So let's say if I'm trying to predict a disease like cancer, for example. If there's no cancer and I declare that if there is cancer and there's a significant cost, they have to go through chemotherapy, like their entire life is going to be like upended. But if they have it, if there is cost to it, but if they have it and they don't, maybe like subsequently, then some other tests are going to pick it up. Okay. So you might need to adjust the cost, or probably in some other situation might be different. Okay. So in practice, usually the cost of this classification of 0 versus 1 is not the same. So this is called cost-sensitive learning. So if you incorporate this cost, then you can say, okay, now what is my optimal classifier? And then you have to redo the argument. And it turns out that nothing really changes except when I'm going to replace this with, we're going to replace this guy with the expectation, Ly and f of x. But yeah, I usually put y hat here, so let's do, it's going to be Lf of x, y. Doesn't matter which way you write it, but to be consistent. So this is that in general, and then the same integral, like the same decomposition applies. The law of, I think this time they call it law of total expectation, if you want. So expect that L of f of x and y given x is equal to x. Okay, and this still holds, and then I'm gonna minimize this quantity. And I'm going to try to minimize that quantity. That's like the conditional cost. So the optimal classifier turns out to be the one that minimizes this conditional cost, sometimes referred to as posterior risk, because its expectation so I'm going to do like L of, replace this with a decision, and y given that x is equal to x, and then d in 0 to 1. So I'm conditioning on x. This is the placeholder for y hat or f of x. So I'm going to choose the decision that minimizes this cost, and this cost can be calculated. And this is the exact same procedure that we did here. So here you replace this with a d and choose the one that minimizes. Here I'm replacing this with a d. And so if you follow this argument, it's exactly the same exact argument we did at optimal classifier in general. So minimizes the posterior risk. And this one you can calculate. You know that here just the randomness is y conditional on x. So if you know the conditional distribution of y given x, you plug in decision 0, you calculate this. You plug in decision 1, you calculate this, and whichever posterior cost is the minimum, it gives you the decision that you have to make. Okay. And this is an exercise for you in the book that, and the lecture notes that I'm going to assign. And you end up showing that like with a minimal change to what we had before, we can do this as well. So you go through this. For the binary case, it's very simple and like hopefully a good exercise. But that's how you calculate the general optimal classifier. Okay, sort of clear. It's a little bit abstract, but nothing very difficult here. It's just that this is now a random variable. It takes two values. You plug in y equals to 0. So the expectation that this is the random variable takes two values. LD and 0 and LD and 1. And it takes them the probabilities of y equal to 1 given x and y equal to 0 given x. So you plug in y, fix d, you plug in y equals 0, it gives you LD of 0 times the probability that y is 0 given x plus LD of 1 times the probability that y is equal to 1 given x. And then you manipulate that, try to see which one of them is smaller. You can do it abstractly and then something interesting comes out. Okay, so this is just an aside that you can do it more generally. For now, we're going to focus on the misclassification rates. Okay. So cost sensitive. And just one little tidbit is that this concept of learning usually comes up alongside another concept, which is imbalance in classes. So usually the two classes are imbalanced in the sense that the fraction of people that have condition y equals 0 is very different than the people that have condition y equal 1. So for example, in our case, the probability of survival, you can see like the probability of not surviving is higher. They're not like 50-50. And in practice, usually, in many interesting examples, like say cancer example, like the majority of people don't have cancer. They're a very tiny fraction that have it. So this would be very, very small. This would be very large. So you're doing the extreme imbalance classification of the practice, and there are going to be problems. And one way people deal with this is they reweight the error to account for that. So they train classifiers to treat the errors differently because you will have very fewer examples here. But I'm not going to go into that. Just a point of practical interest. This guy comes in with like class imbalance. It's not necessarily the best way to deal with this. I would say it's like conceptually not related necessarily, but that's how people do it. Okay, questions? Okay, let's go back to the original problem. What was the original problem? The original problem was that we just had this table, right? In practice, you're not going to be given joint probability distribution, so you can't do any of these calculations. So how do you actually do this in practice? So that's the next step. I'm giving you this data. How do I go and find something like try to approximate that optimal classifier that we derived? I don't have this. No one gives me this, right? They give us this guy, the table with all the data. Yes.
You can use proportion as an estimator of the probability.
Great. Yeah. So that's the simplest, like the most natural thing to do is to use proportions to actually like recover this table or an estimate of this table. In fact, what I did is actually wrote this table out of those proportions. So there is a population level, but I can approximate it by the fact that there's this frequentist interpretation of probability. So what is this probability? The probability that X is female and they survive. In practice, it's close to how many in the sample, how many females actually survive. Okay, so the proportion of all the look at this, all the samples here. For example, we have, let's say 982, and you look at, for example, all the pairs that have these two values survive, and their and that would give you the proportion. You count how many of those cases are divided by the total number. That gives you an estimate, right? How many are male and did not survive? Here you have a lot, right? 1, 2, 3, 4, 5. So let's say my data was just this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10. Let's say that's the most I have. So based on this, what would be our estimate of that table? So it's like female, male, 0, 1. So how do I do that? So female and survived would be 0.1, like 1/10, right? Female, sorry, not this is survive. So 1/10. Female and not survive is also 1/10, right? Is that true? Okay, 1/10. Male and not survive, 1, like 1, 2, 3, 4, 6. Okay, so it would be 6/10, and then male and survive, just 1, right? Oh, like 2, no, 2/10, right? So that's our table. Is that correct? They sum to 10, so like 0.1, 0.1, 0.6, 0.2. Okay, once I have this estimate, then all the machinery works. Now I can compute conditional probabilities. I can compute the optimal classifier. That would be all an estimate, but everything works, and I have it my classifier, right? So the steps to go from like knowing, not knowing to knowing this calculation. And you can see that this is not necessarily that close. It's very interesting. So this is why I have, say, compared. Right. So there are some discrepancies with this is actually calculated based on the entire data, about 1,000. And it's not that accurate, but it's not too far off. So there is some error in the error because of the sampling. So you just use 10 samples. But it would be interesting if you, for example, you can go and calculate the sort of optimal rule. In that case, it would be called the plug-in rule, because we plugged in these estimated probabilities. And then you can calculate, like, it may end up being the exact optimal rule here because of the errors. Like, there are a lot of errors, but maybe they don't change. So I don't have to have like 72 here. Anything above 0.5 will give me the same decision. Anything below 0.5 here will give me the same decision. Although I make a lot of errors in estimation, as long as they don't change this boundary, basically, then I'm going to be good. I may be able to like actually reconstruct the optimal classifier just by 10 samples. So I like encourage you to go through the calculation and see if it's going to change or not. So there is a certain robustness to classification. You may not need like a very huge amount of data. But in any case, as you get more and more data, if I compute it based on this entire table, like 0.9, like 992, I think this is a training sample. It's going to get very close to this. At some point, it's not going to matter. You have more data, your classification is not going to change. Sounds good. These are tricky issues, though, by the way. But if you understand it, if you go through this, it gives you a lot of insight. How many data you actually need to compute this classifier. it might turn out that you don't need the entire table. Just maybe 20, 30 samples is enough. Actually, if you only care about sex and survival. Okay. Sounds good. So we're done. We did the classification. We just did machine learning, and the rest is like basically tweaks on this idea. So the first thing that I want to do, if there are no questions, is to write it a little more formally. So what we did, like calculating the proportions, I want to use math to write it down a little more precisely. The same idea. So you go and count how many combinations of different values you observe. So for each combination, you record how many you observed divided by the total number. So this we can use indicators to represent. So this is the idea of optimal classifier. I'm going to come back maybe to this. So that's this. So in supervised learning, you actually have access to training data. So you observe IID sample from this P. So each pair is an independent draw from P. You can think of it as one row of that table. And then by the law of large numbers, so this is this notation that I have here, or this expression is basically what we just did. So indicator yi equal little y and xi equal little x. So I fix little x and little y. So let's say this is female survived, and then count. So this is counting. So this is going to be like if the ith sample is survived and is female, this is going to be 1. Otherwise, it's going to be 0. So this is that indicator notation, and so this counts how many of my samples are match this criteria. Okay, so that indicator just selects like is 1 when the condition holds 0 otherwise. So we count and then divide by n. That would be my estimate of that probability, and I'm putting the p hat here to denote that. Okay, so the p hat of a generic y from the population is equal to y, x is equal to x. So that's the joint estimate of the joint, and then the estimate of the marginal would be similar. So the marginal of x is what fraction of xi's is equal to little x divided by n. You can also get this by marginalizing out this, so you can sum over all y's here, and this gives you the same thing, because this is a proper probability distribution. This is the marginal, and then I divide the joint by the marginal, I get this conditional probability. Okay, and then 1 over n, you can see the 1 over n's go away, you just divide the counts. And this is also what you do in practice. What this is doing is, I'm going to go look at, for example, if I want to compute the conditional probability, I'm going to look at all the samples that have x not equal to x. I ignore everything else. That's the total number of those samples. And within those, I'm just going to count how many I have this as well. Okay, it's just, so if you do it, for example, in R or Python Pandas, you group by X, and then you like take the average within that group. This is going to be the average within a group of the responses, or like proportion. Average of Y's, we give you proportion within each group. So that's the conditional probability, and then the optimal rule is gonna, for every x, checks different y here, y equals 0, y equals 1, and minimizes. Right, in this case, maximizes this. That would be your plug-in estimate of this, so arg max of this, or arg min. E hat. Y not equal. Why I'm calling it plug-in, because we plugged in the estimate. So this was the rule here that plugged in my estimate, just calculated. So it's a plug-in estimate, or like made it Bayes rule. So and then you can do the calculations for yourself. Maybe I'm not going to repeat that. It's just that for the data, you can do. So our table was like this. You can actually go and calculate 0.1, 0.1, 0.6, 0.2, I guess. And so this would be like, so if, for example, this was y equal 1, given that x is equal to, I don't know, male, this would be, yeah, the counts would be, here we have the counts, which would be like 1, 1, 6, 2. This is counts. This is proportions. So this is, I'm counting how many are both, I think this was not survived, this is survived. No, female. Female, male. This is not survived, survived. So this would be 1, this would be, oh, sorry, this would be 2 divided by 10. Right, so this would be this. The total number is 10. Oh, sorry, the total number is 8. 2 divided by 8, 2 out of 8. There are 8 males, 2 out of them are this, so it's going to be 0.24, 25. And so we still decide, because he had y equal to 1, given x is equal to m is 0.25. The other decision, which is y equal to 0, given x equal to m is 0.75, he decided 0. He declared that he did not survive. For the female, it's very interesting. I remember now. So what happens for the female case? Like, probably that they survived. This was a good example, actually, now that I remember. So decision would be decide 0. In this case, it would be, sorry? 50, yeah, 1 over 2. So there's just 1 that survived out of 2. So it's going to be 0.5, which means that the probability that they did not survive, the estimate would be 0.5. So what would happen here? What should I do? This is a great example of another exercise that you're going to do. So what happens if this probably is 50%? If it's like below 50% or above 50%, you're good. In this case, if we gathered more data, this wouldn't happen. But as it turns out, in this case, this happened. And so this is a corner case. Sometimes referred to as the decision boundary. So we hit the decision boundary. And I'll let you decide, like later, think about what should you do this in this case. Okay. Decide. Exercise. In any case, the idea is that hopefully you have enough data, maybe you don't run into this issue, it's maybe like 0.58 or something, and then you decide 1. And then you have your like classifier. Okay. Sounds good. I'm going to come back to this formula later and then try to massage it into something gradually more interesting. Questions? Comments? Is this clear? So you now can do binary classification using a binary feature. Right. So I want to introduce a couple of notations. So this is for the end of story for this problem. But I want to introduce a couple of notations that we use later. One is that we will give this guy a name. So this is for the actual. So this is another problem that we're going to look at. This probability that y is equal to 1 given x turns out to be important. As you can see, where I can write it as this. I'm going to give it a name. I'm writing it as eta. You can write it like that, given x is equal to little x. So this would be a function of x. If I plug in the random x, it's going to be a dot x. So this is the same as this. A little bit more compact. So this function, the probability of y is equal to 1 given x, is a function of x only. And like a statistician would call it the regression function. Why they would call it regression function? Because it turns out, as we'll show, it's also very simple because already get something like that. But this is also the expectation of y given x. An expectation of y given x in statistics is the regression function. Okay. So in binary classification, the regression function would be just the probability that y is equal to 1 given x. And if I have that, I also have the like 1 minus eta of x is the probability that y is equal to 0 given x. So I have all the information I need to calculate the optimal rule. So the optimal rule, then you can actually show, you might already have seen it, but this formally can show that it can be written in terms of regression. If the eta of x is bigger than 1/2, I decide 1. If it's less than 1/2, I decide 0. This is the optimal thing to do. So once you estimate this regression function, it's going to be your optimal rule. You plug in the regression function like with eta hat. So estimate eta hat x is equal to like p hat. That's the from those like proportion calculations, and then you plug it in here. And you get to classify. But this is the optimal classifier. Optimal classifier classifies based on the value of the regression function. And the decision boundary is where the different function is equal to 1/2. So in the space of x, there is a set such that this eta of x is 1/2. Sometimes this might not be there, but if it's there, this is called the decision boundary, and then you're going to think about what you should do. So I'm not specifying what you should do at that case, but let you decide about what needs to be done. And the way to think about it is you're minimizing the probability of error. So does it matter if I choose one or the other, or if I want to minimize, what should I do? So that's what we want. So what should the value be to minimize the error? You have minimal probability of error, or like misclassification rate. Minimal rates. Okay. So this regression function is going to come up frequently later. Okay. In this case, it's just going to be for every x, I'm going to give you like a probability. And in the problems that we looked at, the two values of x. So this would be really a benefit. Like 0.72 and 19, something like that. But in general, it would be a proper function. If x is continuous, this would be a function, continuous function, more or less. Okay. So regression function, in this case, gives you all the information you need to calculate the optimal classifier. And the optimal classifier just thresholds this. This is like a thresholding rule. Threshold the regression function. That's the deal. Questions? Comments? Okay, one more just comment is, this is, for example, how you can do it in R. As I mentioned, if you group by the feature and I take the mean of survived in that group, this also calculates how many there are. So this gives you the list table. If you don't know the groupier, it's fine. It's just very easy to calculate these proportions in R or in Python. It gives you the initial probabilities, and it gives you the probability that the feature is taking these two values. And then this can be summarized. This is again an output in R, the package, I think R part. So the output can be summarized like this, using a tree. So I have at the root is what happens if I don't use the features. That's the majority rule classifier. 100% of the samples are at the root, And then this 38 is saying 38% have survived. That's the probability of survival. Estimate the probability, and this is the decision. Because the probability of survival is less than, so this is really eta of x, which is the probability of y equal 1 given x. Here there's no x, so it's just here you should say this is really this. Here is just the probability of y equal to 1 estimate. Right, these are all probabilities of survival, so like the label 1. And so here you decide 0. 0 is the decision. So that's y hat equal f of, or in this case, there's no x. So at the root, you decide like this. Now, if I add one feature, 6, then the decision splits, depending on whether you're male or female. When we are male, like this is saying 64% of the population lands here. This is, again, eta hat of male, which is like the probability of y equal 1 given x is equal to male. And this is eta hat of female. Right. These are the things that we calculated up to the numerical error. So we carried 0.72, 0.19. And so 0.72 is bigger than 1/2, so we decide 1 here. And here we decide 0. Okay. So this is an example of a very simple decision. They call it decision trees. And it's one of the most basic classifiers that you can imagine. And then as we get more features, this can be more complicated. So then, for example, I have another feature here, and it splits more based on that feature. Here, it can split more based on that feature. We'll see. And then every data point that you want to classify, you go follow this. Start it's here, and we get the place, which is like, you land here. If it's another feature, you land there, and so on. And then at the end, we decide. At each point, it tells you what your decision should be. It's a very nice way of summarizing this type of classifiers, and it generalizes more. We might not have time to talk about that, most likely, but even if your features are continuous, what you can always do is like discretize. So if I have like age, I can say, okay, I'm gonna look at everyone that's above 20, everyone that's below 20. Okay, that gives me a binary feature. Now I can classify using this. So where should I cut off? Then you can also like try to optimize that. Like 20 might not be the best, so I'm gonna vary that and then choose that. How do I choose it? Based on the loss that we have, the probability of error. So you have the probability of error, you try to estimate the probability of error as you vary that threshold, and then decide the threshold and which feature actually you want to do. So they do what they do in practice, they do it very greedily. So greedily pick one of the features and then choose the threshold. You get the split for that feature, choose another feature, do it, and see which one does better. And then you pick the feature that does better first, and then repeat. Maybe we'll talk about that later. But the basic idea is very simple. Once you understand this, they're trying to approximate this. For discrete, like binary labels, there's no thresholding going on. It's perfect. So I say the first classifiers that you should learn are majority classifiers, and decision trees. Okay, we'll see a more complicated example. But this basically summarizes these conditional probabilities as you go along. An example of a decision tree. A decision tree summarizes conditional probabilities and decisions as we go along. especially useful when you deal with categorical variables. Questions, comments? All good? Okay, now a glimpse of local averaging. So this is another exercise. I may assign it. So we've seen the regression function. You've seen this estimated regression function. We did this calculation. The indicator, I'm going to write it the other way around. Xi equal to x, yi equal to y, little y, divide by I from 1 to n. Xi is equal to x. So I wrote it like this. But in the binary case, you can show the thing you just as well rewrite this part as this, because y only takes value 1. Okay, so yeah. So this is for a general y. So if I said y equal to 1, this is going to be 1. yi equal to 1 is really yi itself. And then we think a little bit about it. I just write it like that. And it's like a very easy exercise. So we write it like that. And then I can, what I can do is, this thing is like a constant. I can bring it inside. And I don't want to do it for you. So an exercise, very simple exercise, you can rewrite this in this form. Okay, so there's going to be a summation. And there are these weights here that you specify. Just this goes to this. That depends only on x, and then they weight yi's. So what this is saying is that for any observation, I have some weights, how I weight the training data yi, and that gives me my prediction for this probability, or like my estimate of the probability. So different x's would just weight different y's differently. And as we'll see, this is going to be like a similarity image. How similar this particular x is to the xi of yi. So turns out, just if I want to say it, it's just that's the weight. Let's bring it in. But this just measures how much x is similar to the x of the I sample. And if it's very similar, then I'm going to include that yi. If it's not too similar, I'm going to downgrade it. So this calculation that we did is really a weighted averaging estimator. And it's a local averaging because it just depends on the particular x. The weights are not fixed. I'm not just averaging all the y's. For different x, they weight the training data differently. And if you dig into this, we'll come back to this. And once you do this, this is really measuring this form of similarity. In this case, similarity is the exact similarity. If my little x is actually equal to that particular xi includes yi, if it's not, I'm going to include it. But once you view it like this, then you can generalize. You can relax the similarity from exact to approximate, and also the interesting things would come out of it. Okay. Sounds good. Just do this exercise for yourself. It's very simple, but very useful. We'll come back to this formula. Basically, if you replace this with something else, you get a different. Yes.
I'll just clarify if I understand what you're saying with the x's as translated to weights here.
Yes.
So you have a binary x.
Yes.
Then the weight would either be 1 over the number of rows.
Yes.
With
Yes.
x equals that value or 0.
Yes.
And
yes.
so you'd weight all like relevant x's equally.
In this particular case, you're right. Yeah. So let's say you fix you fix little x, right? All the xi's in the training then will have the same x. Will have the same maybe 1 over total number of them. Right? So you basically in this particular case, you just average all the usual average, all the yi's for which xi is equal to x. but you can do more, like later you can replace it. Yeah, but that's exactly what happens. So you go in your data, let's say I give you male, you go look at all the males, you just average the yi's. That's what we did actually. That gives you the conditional probability. That's it. If you have actually more levels, that's exactly what you do again. So you have like multiple, the feature has multiple, we're going to do that in a few seconds, but let's say you have 4 levels, you go in each level. If like, I want to predict, for example, based on the P class, that's in the class 1, 2, 3. So if I observe class 2, I want to predict class 2, I'm going to look at everyone that has class 2 and average the y. If I'm going to go predict the class 3, I'm going to look at all the ones that have class 3 and average the yi's. So everyone, like, everyone gets the same weight in this case. But the general form is more interesting. So later, when x is continuous, there's no exact corresponding. So it's not like I'm going to find exactly the same x in my data. So then I have to decide who I should average over. And then you define a similarity measure, the people that are close in x, I'm going to average over. And that leads to like k-nearest neighbors, like other estimators. Sounds good? Okay. So as you can see, this example is simple, but there are a lot of like glimpses of all the more complicated stuff, more interesting stuff in there. Okay, so what I want to do now is, so we have the estimate, we've estimated the joint, and then we estimated the regression function, estimated the like plugin, got the plugin rule. So now the question is, how do I estimate the error? Okay, so I want to also have an estimate of the performance. I want to also estimate it based on the data. So what is the obvious way of doing it? So if I have what I want, basically an estimate of this quantity probability of error. Remember this py not equal to y hat. How do you estimate? Or the risk in general. How do we estimate something like this? It's a probability or an expectation. It's still, you can use your estimated probabilities to calculate this. As if you recall, calculating this two-way based on the joint distribution or the conditionals, and you now have all of those. So you can go use your table that you estimated probabilities from, and then calculate this based on that by the conditioning or from the joint. And so what will happen is effectively you replace this with the averaging again. So you 1 over n summation I from 1 to n indicator is going to be yi not equal to f of xi. So you're going to go look at all your data, apply f to each xi, and see if it matches with yi or count how many times you make the error. So that's like a methodology empirical estimate. So that's going to be this. But there's an issue here, which we have to be careful. So this is going to be referred to as a training error. If you're going to use, so this is natural, right? So you replace your estimate of like the probability, the estimate of probability based on like the fractions. Okay, so I have, you can imagine this is exactly the probability estimate of the probability. The issue is this f hat is also using those same samples. Okay. Why this would be an issue? Anyone knows why this might be an issue? This is perhaps the most interesting or tricky thing in probability prediction machine learning, supervised machine learning. But this training, this is an estimate of the error, but this might not be a good estimate. We usually underestimate the risk, the actual population risk. Not in this particular case, but anyone has seen this? This is called the training error. because I'm evaluating the classifier on the same data that I use to drive it. Okay, so let's say I give you the table, you use all that information to calculate the joint. Let's predict the estimate the joint, calculated the rule, that decision tree, whatever that we have. Now you're using the same data to evaluate. And we apply our rule to each row again, and then count how many times we make the error divided by the total number. So that would be an estimate of the risk. It is an estimate, but you have to be careful. Anyone? Yes.
Overshooting.
Overshooting. Maybe what is the term? It's gonna overshoot or undershoot, generally undershoot or underestimate. But what they're saying usually like overfitting, right? Is that the term usually they say is overfit. So, but overfitting is related to this. The overfitting is when you choose your classifier based on trying to minimize this. Then people say you often overfit. Maybe I'll get to that. But at this point, so technically, if you think about it, we actually chose our classifier to try to minimize this. If you really think about it, the procedure that I went through tries to minimize the probability of error. What I'm actually doing in practice, I'm trying to minimize this estimated probability of error by doing the calculations that I did. So I really chose the classifier to minimize this quantity. This is a little bit subtle, right? So we didn't go through this directly, but if you do all the arguments that I did for optimal classifier, replace P with P hat, really the estimator that I got out of this guy or this guy, the decision rule that is based on this is going to minimize this quantity. And whenever you try to minimize this, if your function, like in this case, the function is the function class, the number of functions that we work with is small. If you recall, how many functions we deal with, how many classifiers, potential classifiers we are looking at. Four, yeah, 2 to the 2. So we are looking at 4, and that's fine. But if I was looking at 2 to the like 10,000, there are too many functions, and I might be able to actually drive this to 0. And if I minimize it, I might be actually be able to make it equal to 0. But that's not what I want to do, because the actual thing that I want to do is the population risk. And I haven't seen all the data. Right? I haven't seen all the data. If I minimize this, maybe in the future data, I'm going to do worse. Okay, because there is some noise in this particular value. This is not the exact probability, it's approximate probability because of the error in the number of like finite samples. So this is not the thing that I want to do. This is the true thing plus some error from something. And if I drive this to 0, I'm actually driving the noise. I'm trying to fit to the noisy part as well. And that's where you think overfitting like it. Okay, so this quantity is surrogate for what I want to do. And so you really don't want to drive this down to 0. But that's what will happen if you do this procedure and you actually the number of functions is large. In this particular example, which is very interesting, because there are not that many functions, I can't overfit that much. So if n is large, let's say 1,000 here, this is still going to be good. But that's very subtle. So I don't want you to, that's like level 3 or 4. Like level 1 is understanding that this is bad. So you shouldn't try to minimize this in general. Okay, so we're out of time. I'll come back next time and talk about what we're. Thank you guys.